Hey, what's going on, folks? It's Mike here, and welcome back to my Deep Programming Language series. In this episode, I'm going to be showing you a lecture that I gave as part of my Systems Programming course. Now, at this point in the semester in my course, we're giving students the option to use a language other than C to complete their assignments. So we talk about in this course other systems programming languages like D, which I'm going to be presenting here, and you'll get to see Rust, C++, and so on, just to talk about some of the trade-offs of different systems programming languages that exist, why they exist, and so on. But this lecture, you'll get an overview of the D programming language. So if you've been watching this series from start to finish, you'll see a lot of things that, well, probably you already know. So hopefully this will be a nice overview for you. And if you're just joining this series, hopefully this will be a nice overview of what the D programming language is, why I like it, why I think it's a safer language to use, and maybe you'll learn some neat tricks and be encouraged to try D yourself. So with that said, let's go ahead and sit back, relax, and enjoy. And just one little note, I was a little bit sick in this lecture, so hopefully you'll just enjoy or make it through with my voice. But anyways, with that said, enjoy the lecture. Hopefully you learned some cool things, and let me know what some of those things are that you learned below. And with that said, let's go ahead and get into it. And I want to go ahead and show you, since we're talking about the D programming language, where I'm going to basically give you 75 minutes of deprogramming experience here from the sort of systems perspective. We may not get through every example, but you'll have this to evaluate the D language. But one thing I did want to talk about is the community. D is obviously a smaller programming language, but there are conferences. There's multiple conferences a year in D. And if I wind us back just a little bit to 2023, I did bring a few of my students at my former institution with me. So you get an all expenses, not that it's super lavish or anything, but you get lodging and airfare, reimbursed to come to London and give a presentation. So this was in 2023. We did that with some former students. So you might check out DConf. Here it was in 2025. Again, historically, it's been in London, so that's a nice little reward if you end up liking the D programming language and doing something in it. There's the Symmetry Autumn of Code. There's Google Summer of Code. These are other ways to get paid and work in or on the language, which are also great ways to get mentorship. I have a few of my senior thesis students working with some of these people in the D community as well. And maybe they'll make it to London, which would be really, really exciting. So anyways, just some things for you to think about now or in the future. And in some of my other courses, I use the D programming language for me. You might learn about Rust being used in other programming courses here as well. So definitely take a look at both these languages. There's a reason we're taking the time to show you here in systems each of these languages. So without further ado, let's go ahead and move on here. Already talked about the logistics. Again, the allocator stuff we've been talking about. This will be useful for your problem set number 7. Again, emphasizing that we need to do some sort of bookkeeping every time that we do a malloc or calloc, basically, so we know when we free what blocks to free. So we talked a lot about that last time. There's many different strategies for the different allocators that we have. Monotonic, pool allocators, trees, linked lists, arenas, and so on, different strategies, and of course our global general purpose allocators. But along with these come some challenges, and maybe each of these different strategies can help us address some of these challenges, things like fragmentation, which we spent some time talking about. You can see how the different memory access patterns based on how we malloc and free, and maybe our different strategies, meaning if we're using first fit, best fit, next fit, etc., could lead to fragmentation, where we have places in memory where we couldn't fit a block. That is, again, our bookkeeping structure of memory with the actual allocation. So that leaves gaps in our memory, and that's really bad for things like performance. We're hurting locality, right? Spatial locality when we do this. We're wasting resources. So again, we want to do a nice job or choose from a number of allocation strategies to fix this. As I alluded to, we'll talk about potentially do another allocator assignment after, where we can split and coalesce these blocks, combine the blocks to do a better job of ridding the fragmentation, perhaps when we do the free operation, for instance. So anyways, just keep an eye on that to make sure you're familiar with that material, and we'll be good to go here. Now, again, getting into the D programming language, if you choose to use this for your allocator or otherwise, this is your slide deck for it. We might not get through everything. I want to do a little bit of live coding just so you can kind of see how the language works, get a feel for it. But otherwise, this will be a nice preview. And then, of course, if you take other courses with me, you'll get a chance to do a little bit more of a formal preview, let's say. But here we go. Let's get our first impression of the language here. And what I'll ask you to do is just go ahead and hit that space bar and pause the video and see, what do you think of this program? What does it do? What's interesting about it? And if you pause the video and did that exercise, well, let's just find out. Let's actually just crack open a terminal here. And as I said, I want to do a little bit of live coding with you with the language. I don't want to take up all of our time, but it is fun to try out. But again, just sort of working our way through the program here, we have the main function. You'll notice it's void main, so there's no return value. You can return a value, of course, if I make this int main, but it doesn't have to be required. So that's something that's new. The next thing that's sort of interesting is I'm importing these standard libraries, things like algorithm and standard IO. So D has many of the same library names for things that you were used to already in C, stdio, standard IO, but of course with the standard dot in front of it, std, again from the standard library, which we'll learn is called Phobos later on. Well, again, what's also interesting is I see these imports here. They're within this scope here. So I can have these imports scoped locally. That's kind of a nice thing for refactoring. If you're more comfortable and want to put them above here, you can. I'm going to leave them local just because it's something new. And then, you know, if I refactor this main function, I can just manage the imports here, which is kind of nice here. Now let's go ahead and do this next line here, starting program dot write line. Looks like things are a little bit backwards and there's no parentheses. I can omit those if there are no arguments. That's kind of nice. Maybe it bothers you. Maybe you're wondering if that's a variable or not. But I actually like this when we start chaining things together, which we'll talk about here. But this is one strategy. And if it makes you more comfortable, we can also just write this as hello systems people, something like that here. That's how you could write the function quote unquote normally, let's say. But to each your own, you can read this left to right by just taking out the first argument and popping it in front here. So that might be something new if you're coming from C only. Then we've got this here, enum. What is this here? Well, it looks like I've got an array of values here, 3, 1, 2, 4, 0. Very nice here. And basically what an enum is a compile time value. Okay, what does that mean? Well, you know, if you've used enums in C, these could be things like, you know, I could have an enum for the days of the week, things like Monday, Tuesday, Wednesday, Thursday, etc., so that I don't have to assign them values. In C, an enum would reduce to an actual integer value, but this is something that I fully have available as a compile time variable. So it could be an array, it could just be some value like this, 3.1. Oops, let me make sure I get pi right. You know, something like that here, 1415, whatever pi is. Yeah, then this value is available at compile time. So this is a big part of the D programming language, other languages like Rust as well. How you have basically guarantees at compile time that, yes, I have this value available. I can use it in calculations. I can run functions at compile time. Let's go ahead and just see a little bit more about that. I'll get rid of the pi thing because that's not relevant, because let's just go ahead and use this. Static immutable b equals sort a. And then I'm going to use this pragma here, which is basically a instruction to the compiler, so something that happens at compile time. And I'm just going to print out finished compilation and b here, okay? Okay, so a few interesting things. You're probably wondering what the pragma is. Maybe you've seen this in your C code, pragma once or something like that. But in D, let's go ahead and use the D compiler. You can see what I have here. Again, if you're a Yale student, you should be able to check this out on the zoo. We have the compilers installed, or you can download this. I'll show you later. D has its own reference compiler. There's also LDC. Let's see, I don't have it installed right now, I guess. And there's also GDC. And these are the GCC-based compilers and the LLVM or Clang-based compilers, okay? But anyways, let's just go ahead and use DMD to compile this file here, exercise.d. And I'm going to go ahead and output it. And, well, that's kind of interesting. I just compiled the program, and it printed out this pragma here. So this is showing or proving to you that I can do something at compile time, which is really, really super cool. If I can do stuff at compile time, that saves you, the user, time when you're actually running your program. Also at compile time, that's a great time to catch errors, right? While I, the developer, am developing the software. That's why I want to be able to capture these errors there. So compile time programming is a big thing in modern languages. And it's also a big thing because we have defined behavior. I mean, the behavior has to be defined because we're compiling the actual software. Now, when we're running our program, who knows what's going to happen, right? What option the user is going to do, how they're going to use the program, what other processes are running, and so on. So anyways, this is kind of a neat thing that I can, do actual computation. And I'll tell you, there's nothing special about sort here. This is a function I could call at runtime or at compile time. It doesn't matter, but I get access to it both places, which is super, super powerful because I just saved the user the work of having to sort this thing here. Okay. Now, let's go ahead and just show you sort of the difference here, and you can get a little bit familiar with the language. Again, some of the things we're going to see in the slides later. And let's just say I want to create a array here. Let's just call array here of the same thing, 3, 1, 2, 4, 0. And then I want to do write line finished runtime. And then I'll just print out that array. Let's actually sort it. Let's put it in here, something like that. Let's compile. And again, you won't see any of these write line messages pop up until I actually run the compiled executable program. And then now you'll actually see our messages. Starring program, which is, well, starting spelled wrong here. Let's go ahead and fix that. That's our first message written out. And then hello systems people, and then finish runtime. And then again, we get our sorted array. The same thing, but this is the runtime array. This is the compile time array. Now, again, I didn't really need to pay any, I shouldn't have had to pay anything, so to speak here, because I already had this array at compile time sorted, right? So I could actually just use this here. Now let's go ahead and just comment this out here and do write line. The already sorted array at compile time. Let's go ahead and just put it on a different message here. B here. Okay, let's go ahead and try this out. Let's compile it. Let's run it, and then you can see what it is here. Now, the already sorted array at compile time is giving you kind of a weird value here. I can see the 0, 1, 2, 3, 4, but it's giving me the full type here in the right line. It's this immutable sorted range that's of this type here, which looks like a dynamic array. And that's exactly what this is, an array that I can resize. And then it gives us, some of the other things that it knows at or knew at compile time from this type. And you might say, well, that's kind of ugly. So let's just do another little import here. And when I sort this thing, let's just convert it to an array here. Okay, something like this here. Let's see, that compiles, and then when I run it, that looks a little bit better here. Okay, two things that were interesting here. Again, just giving you a high-level view of the language. Dot array converted this into an array type here. That's something that's handy. And D has ranges. It uses something known as ranges. Which if you've used Python, like a for each loop, well, D has those as well. We could say something like for each element in B, write line, I don't know, let's just write out the element just so you can see what's going on here. Compile it, run it, and again, you can see the little for each loop here. And a range is something like, it has a beginning and an end, so to speak, so we can iterate through it. So that's why you were seeing the weird type here previously, but I just converted it to an array, so you don't really have to worry about that. Arrays are ranges, whole thing, we can get into that. But anyways, nice, little intro to language. We have for each loops, we have regular for loops, and a lot of the other stuff that you're used to, but hopefully this gives you a feel of the language and some compile time stuff. Now, this immutable variable is like const, this qualifier here, but it's much, much stronger here. That's why we had to actually convert this into an array, something that's, that I could do something with at this point in time here. But anyways, immutable is basically a stronger guarantee than const, and I'll get into that later. Static kind of means the same thing as in C. There's a few meanings of it, but it means that we'll have this available in our binary, right, within the scope. And you'll notice that there isn't a type otherwise because D is smart enough to infer some of these types here. Okay, so I could have also done something like this here, auto, instead of the type. So, you get some of these nice conveniences and, the program still works the same here. Okay, so I think we get the idea. Hopefully you observed a few of those things here. Here's just a little recap here. So again, we have our libraries, We've got this neat uniform function call syntax, the enums that we talked about, immutable static values, and of course the pragma. And we've got other things here. D does a neat job with arrays. There are dynamic arrays. There's also fixed size arrays. And you always have dot length and pointer together. This is a big deal. This is a big deal in systems programming because this helps us prevent buffer overflows. Okay, we always know the size of our arrays. They don't decompose when we pass arrays and functions into pointers like in C. We always know length and pointers. Sometimes we call this a fat pointer, so to speak, because it's always got these two attributes associated with them. Okay, and I talked a little bit about the compile time programming here. Okay, so what is the D programming language? You got to see a preview of it, but it's a general purpose language. It's going to got C-like syntax. You're going to be familiar with it, and it's for writing fast code, reading fast code, and running fast code. Okay, so anyways, it borrows the D programming language from a lot of different languages. You can see some of the different examples here. I'm willing to bet that you could read this code if you just stare at it for a moment or two. You know, you would get the gist here. And it's got some built-in types. We already saw the arrays. I mean, in C we have arrays, but in D we also have dynamic arrays built in. We have things like maps built in, which use the same sort of syntax. So that's very, very nice and convenient. So sometimes it feels like Python code, which is neat. It is a compiled language. We are generating machine code. You saw me go through that process of using the DMD compiler to get a executable, just like we've been doing with the C programming language. And again, seeing you know, the actual executable code run on my machine here. And of course, you get the compile time function execution. That was, well, if I just bring this up here, that was what was going on at this line here, or with my pragma. So there's a little interpreter inside of the D compiler that's actually, you know, doing some of these operations, okay, so that we get the actual values. Now, D itself is a language that kind of scales with you. It supports many different programming paradigms. If you're coming from the C world, again, you're, you know, kind of just in a procedural paradigm. In C++, you get a bunch of these other paradigms as well. But again, D can write object-oriented stuff. So there's classes and structs and so on. There's functional things that we're going to find out. And again, for writing parallel code, D has kind of prepared us in the future. So anyways, let's see here. In general, I think D was also designed in mind to have a very nice syntax. I mean, I know that's the case, that's been an important consideration here. So you're not usually fighting the language too hard to use different paradigms, which is very, very nice. Now, on the system side of things, one of the things that we're here for is what makes D kind of nice. You know, it gives us the right defaults. So there's a few neat things here. You know, all of your variables are default initialized. So, you know, you never have to worry that you're going to have garbage values or sensitive values left over in the stack. They'll get default initialized. It's a systems programming language, though, so you can turn that feature off if you want, but you need to be explicit if you want the unsafe thing, right? You set a variable to equal void. As mentioned, arrays store pointer and length. So that means you can bounds check all of your arrays. And again, it's a systems programming language. You can turn this off to save performance, but the default is to be safe. We get memory safety by default with a garbage collector. So that means if memory's in use, you can, you know, you don't have to worry about basically null pointer references and these things as much. You know, you have to try a little harder to get those errors. Memory corruption, you know, issues and these types of things. Again, you basically get the memory safety because garbage collector is going to take care of allocating and freeing the memory for you, okay, which is really, really nice. Properties like const and immutable as well are transitive. So that means it's, well, the saying turtles all the way down, as the programming saying, or as Walter Bright, the creator of the D programming language, says, that basically means if I pass some const value or some const pointer or something into a function and then into another function that uses another function, it's const all the way down. You don't like lose track of that qualifier. Okay, it doesn't get like accidentally omitted. So the type system in D is a lot stronger than C or even C++. I don't know if I'd say it's as strong as Rust when you learn about Rust, but again, it is very, very strong. Variables are thread local. This will matter more when we talk about threads and concurrency later on in our course. You can, of course, create just regular global variables like you could in C, but basically this means if I write concurrent code, I have less issues with sharing, so that's kind of nice. Casts always are explicit, almost always explicit. So there's fewer surprises. Structs are value types and classes are reference types. I'll get into that more. And there's safety annotations. So @safe code, for instance, or @safe functions can only call into other @safe functions. Maybe stuff that you formally verified or doesn't do dangerous things like pointer arithmetic. And it is ABI compatible with C. I put this under safety, or maybe more under the productivity side, because again, most languages need to be able to talk to C and C libraries. There's other little things that have been improved. For instance, when you declare variables in D, this produces 2 integer pointers. In C, this will produce 1 integer pointer, and then the Y will just be an int type, which could be confusing. And then in C, you can assign an integer or some address value or something and get very, very weird behavior. So anyways, the D compiler catches a bunch of these little things here. There's also other little things like if you have a switch statement over in enum, it makes sure it'll check all the cases. So again, the compiler is just going to be a little bit more friendly to you and give you potentially better error messages. Okay, so anyways, we're going to get into some more of these things here. A lot of these habits that I've learned, and this is why you should consider trying D, or again, the other option we're giving you in this course is Rust, because it will, some of these habits you learn in these other languages will help you write better code. So I still write some C++ code these days, and again, from D, I've learned a bunch of these niceties that have made my code safer, better, etc. Oops, let me go back here. Okay, so some other things in the D programming language. I'll go through some of these a little bit faster here, but there is a script interpreter here. So what does that mean? Well, this example here, exercise.d, I could just skip that compilation step and just basically run it like a scripting language, right? You'll see it'll compile and run, and it'll actually cache the executable here so that the second time I run it, if you observe, well, let's go ahead and observe this here. It'll actually be cached if nothing changed here, so you won't see that compilation step here. But that basically enables script-like behavior. So that's kind of cool. And this is how I first started using the D programming language to replace a lot of my Python code by writing D, files here and running or using them like a script. They're still compiled, so they're still fast. So you still get the executable speed performance, and this is kind of a neat thing here. So again, here's an example as using this as a script, right? So you can just give yourself permission on the script, and then I can just do / whatever the D file name is, and if I write a little script like this, I can use that. So that's a nice, neat way to use the D programming language. I think it's a nice gateway into the D programming language, so to speak. All right, a little bit of history here. So, we looked at the D programming language already. I kind of jumped the gun into it, but again, what is it? I should know a little bit of the history here. It was created by Walter Bright, who, famously has created a bunch of the C++, first, as far as we know, first C++ compiler all by himself, Zortek C++ compiler. He also wrote in some C compilers, and I think he's also written some JavaScript compilers as well. So anyways, he's an expert at building compilers. And anyways, around 1999 or so, to 2006, eventually he released the first version of the D programming language. That's when he was working on it. And then the other person who gets a lot of credit, Andrei Alexandrescu, a big name in the C++ community, had written a few books. He was working on his own programming language, and so to speak, Walter and him got together and combined forces and, worked on D2, which is what we're using today, and has been the language that has been steadily improving over time. So anyways, you can learn about the history. There's me at DConf with Walter and some other folks in the D community, so... Anyways, so you can learn about that history there. Mike Parker's one of the other folks, has written some books. Anyways, what I want to say about this is the D programming language is, in fact, that language that comes after C in the alphabet, but it's also how should I say still evolving. It's still a language that is actively worked on. Every day you can check out the GitHub compiler, and there's usually different like commits and so on. So it's constantly improving. It's been around for a long time, which is kind of cool. So. And it has lots of these features, which we're going to get into today. So, it's got a full standard library. It's got some of the other stuff you would maybe expect, JSON parsers. You can make network calls. There's a wrapper around, curl and sockets and stuff, which we're going to talk about. Again, multiple paradigm. And again, we already saw the compile time execution, which is very, very useful. So again, you can pick and choose some of these features, but they're nice things. So anyways, let's get into the language. And I'm going to give you the warp speed tour of this, so to speak, here. So again, we've got our basic types, but one nice thing is the basic types are always known size. As some of you might recall from an earlier lecture, when I ask you how big is an integer, it might be 2 bits or 2 bytes, it might be 4 bytes. Indeed, the primitive types are always fixed size. So what you see in this table here is the default value that they're initialized to and how many bits they take, which is really, really nice, because then, if you're trying to write portable code, you know that, again, an integer is always 4 bytes. So you can go ahead and check that. You can print out the properties here, size of, similar things that we know how to do in a language like C or C++. And again, you can see the default initialized values as well with a dot in it if you want to check those things out. Now, one little gotcha here, floating point, the default type is nan, not a number. I like that. This takes some getting used to. Some folks still don't like it, but basically what it means to me is, well, if I'm initializing some floating point value, I should do that as a programmer. And if I don't, I want to catch that error fast, right? I can have an assert in my code to check for not a number, basically nan. And these are very easy to catch, but again, if you're initializing a value and you don't know what the value is, you should have some idea what the correct default is. Is it 0? Well, sometimes 0 is a value you want. So anyways, that's the point of that there. Now that, again, catches folks off by surprise, but it is something I just wanted to mention here. So anyways, you can find all the defaults as needed in the language specification. And again, D in this way has helped me write more secure C++ code, right? One of the main things is always initialize your objects, always initialize your variables. There is a cost to it, but the cost is so minimal. And in C++ and other languages like C, you can harden basically the standard libraries or the compilers to check for these things. But again, this just prevents garbage from getting in your code. Now, again, in D, you can assign things to equal void. So if you have some large buffer of data that you don't want to pay the cost of initializing everything to zeros, you can do that. But, no problem there. All right, const, as we mentioned, we have this just like in C, so it should be relatively familiar. I'm going to leave that as is. It is transitive, but we have immutable. Immutable is a little bit stronger. And a lot of languages have chosen this to be the default. In D, it's not the default, or at least not yet. There are some flags where maybe you can play around with making that the default. But basically, immutable is stronger. It's much stronger. And basically, if I move a slide ahead, immutable provides stronger guarantees than const. So, let me draw your attention to like line number 9 here. If I have something that's a const pointer to some data, right? So I'm pointing to some data, and then the thing that it points to is what's const, right? It'll always point to data 1 here, but I can change data 1. So, is this thing really immutable? No. I mean, what it points to is constant, okay? But I can change the underlying data. So that's an example of one of the things that immutable gets me, where if I say, okay, here's an example, data equals 42, okay, and I try to change, or here's data 3 here, and I say, okay, give me this immutable data here to the address of P3. I can't change data 3. I can't change the underlying, thing that I'm pointing to, because it itself must be immutable, right? Because it has an immutable pointer. So you get some stronger guarantees here. And why is this important? Well, one, it's important for compile time things like we do. We know it's not going to change, so I can compute something with it at compile time. The compiler has that information. Right, we learned about compiler optimizations earlier in this term, things like constant propagation. Well, here you go. It's immutable. It's not changing. I can propagate that value, maybe even get rid of it once it's been propagated. And then, of course, this example here, where I know this is a read-only value, and read-only values become important in concurrency because then I never have to protect that value. I know it's just read-only. It's not going to change. No other process is going to come and mess with that value in between while I'm reading from it. That's the basic idea, right? There's no writes that can happen to a value. So anyways, we're getting concurrency stuff that'll make a little bit more sense. Speaking of concurrency, we have a shared qualifier, which in D programs means that a variable can be shared, okay? That we actually can look at that memory, we can access it from separate threads. So again, it's explicit, it can be type checked. This is a nice thing here in the D language. Enum we took a look at already. It has a little bit of a different, I mean, it sort of serves the same purpose as what you have in other languages, but the important thing being, like, when I make something in enum, that means that it's usually, got to be something that's available at compile time, whether it is a array of values, maybe it's just one value, maybe I'm computing something with it, maybe it's a dictionary. These are all different things that we could have at compile time. So anyways, so here's an example of just some of those enum things. Let's talk about functions in the language. A few things that might be new if you're coming from, again, a C background or looking at this. We can have local functions, so nested functions within each other. Yeah, I know some of you might have ventured into GCC extensions this term and seen that you can do stuff like this, but having or being able to scope a function or write a little helper function is quite handy. More importantly, what we have in D are actual lambda functions. So these are, these can be unnamed functions, or, you can assign them to a type as we're showing here, to the different syntax, just to show you a short form and a long form. And we can pass those functions as parameters into other functions. So you have higher order functions here. So for those of you who have taken courses on, like, say, Racket or, Scheme, pick your favorite functional programming language, this is something that you have here, the ability to just be able to define functions and be able to use them, right? So this is often handy when you're passing a function and a function to define a new behavior. Okay, so here's an example of a higher order function. What I mean about that, not trying to make this a programming language course here, but here are an add and subtract functions, and I have this operation perform, which takes in a function pointer. In D, you just use the keyword function instead of the pointer syntax like you would in C. And it can take in any function that returns an integer, like add or subtract, has two parameters, like add or subtract, and it's just referred to within this function as func or function. So it's just going to perform the addition or the subtraction as shown here. So that's kind of nice. And then all of a sudden I can just, as a user, make different function calls here and change the parameter by the function I'm passing in. So that's what we mean by higher order functions. We also have delegates in the D programming language, which can get the scope outside of a function. So the context around it, the other local scope. If you have other variables, you can read about that, but that's a nice thing to have as well. Okay, let's get into some other stuff. Uniform function call syntax, UFCS. And basically this is what I showed you earlier, where you can chain together functions. So I don't know about you, but I've made errors before where I can't keep track of the parentheses or how nested something is, or maybe it just takes me a long time to type out. But certainly this at line 15 is easier to read than what I see at line 8, where I've got this map here. What is map? Well, map is basically something that says, hey, apply this operation, a times 2. So basically take 1, 2, and 3, treat those as a, and multiply those. That's kind of like this shortened lambda, basically, that we just learned about. And I can just multiply each of the values here. So that's what map is doing. Now, again, it's kind of hard to figure out what that is, going on here when I have like this map, and then what am I mapping this function to? Okay, this array of 1, 2, 3. Okay, this isn't the worst thing in the world, but you could see how these maybe get more interesting. I mean, let's just go ahead and do it in our little playground here. Let's comment this out. I'll just preserve this for our history. Let's comment it out and hide it. And let's do this little example here. I've already included standard algorithm, or previously. Let's go ahead and just include it again. I can do these on the same line too, just to save us a little bit of space here. But again, UFCS. Actually, let's just do this. Let's just do this as a one-liner. We don't even need this. 1, 2, 3. Then I'm going to map here. I'll explain what the exclamation mark is, but that's basically a template. And then I'll write the line out here. Okay, so here we go. Something like this. That's all we need, right? I can even take the right line here and chain this together, right? And that's what the uniform function call syntax is. So you can write a lot of nice one-liners here, and this is easy to read, left to right. 1, 2, 3. Okay, I'm going to map whatever the value is that I read in one at a time. 1, 2, and 3. And then each time that's going to be produced in this array, and then I'll write out the array. Okay, that's the basic idea. Map you can kind of think about as a tool, if you're not familiar with it in the functional world, as an ability to, you could probably replace most of your loops with map. That's kind of what we're doing when I have a for each loop, right? I could rewrite this as for each, let's see, value, 1, 2, 3, you can pass in a range, something like this. And then we would just write, let's just do right here. Value times 2, because that's basically what we're doing here. Then I might need to write line at the end, something like that. That gives us the same thing here, if I get my commas right. And my brackets and so on. So anyways, something like this, would be the equivalent code here, right? And then you can write the nice code to make sure you don't get a comma at the end or whatever. But that's the idea here. Okay, so this, I would argue, is nice and easy to read. Overall here. Here's another example, just showing you some more of what you can do and how it's handy to be able to chain these together. You can chain them up and down or whatever. I don't know why I nested these within the right line, because clearly I showed you could get rid of those. So anyways, we can do better and get these into truly one-liners. Okay, so getting into some other interesting stuff, features, pure functions. There's a whole bunch of stuff you can do with functions, pure functions. Let me work my way from the bottom here, because I know I talked about this already in our systems course. Memoization, I can go ahead and just explore here. But basically this idea here is, when we talked about compiler optimizations, one of the things you can do is change the algorithm and trade some space for time. And if I've already computed some value, then I can save it, right? So in D, you can build that in with memoize, is basically a way to do that. So you can see a function with a particular set of inputs, just record what that is. So if I have an add function with 2 and 7, run it, memoize it, which is basically like save basically that value, and give me 9 back. 2 plus 7 is 9, an add function. I don't know if they have an example here. They do the kind of classic thing with the Fibonacci sequence, but this is how it could look like in D. You could write your own table in your storage if you want, but basically this is just memoizing internally within this function fib here all the values here, right? And then you can compute larger values much faster. Okay, so anyways, those are some things that are built in functional style things for performance. Lazy evaluation. This is especially important for ranges. Maybe you have an infinite range of values, right? Where would you have that? Well, you're writing some streaming service and that's just bringing in values. What do I mean by streaming service? I mean like data is just coming in. Facebook, WhatsApp messages are just streaming in. You don't know how many, but as they come in, you want to process them lazily. And you could have an infinite stream, so to speak. So anyways, you have a lazy evaluation or control of that, and then purity, which I'm going to get into. So what's a pure function? Why is this important? Why do we care as a systems programmer? Well, function purity is an important part of functional programming. My Haskell programming folks understand that, but basically I can annotate a function as pure, as shown on this screen here. And basically what it means is that, well, for a strongly pure function, the same inputs are going to generate the same output. Okay, why is that nice? Well, it's nice because it's probably something that I can then memoize. I can store the value in a table. That's nice. I know it doesn't have side effects, so that might tell me something about how I can use the actual values. Maybe the compiler can do something with it as well. but again, this might also tell me something about, again, in the concurrency world, how I can call these functions without having to worry about race conditions and these types of things. So pure functions are a thing that you can annotate. When it comes to writing tests, unit tests, which I'll get to, this is also important. So to know that there's no side effects or mutations in your program. Okay. So we're still running through features. We still got a bunch of more features to run through, so we're going to continue our warp tour. I know it's a lot of stuff, but hopefully it's interesting stuff. So let me just show you how static arrays work. Yes, I have the notes here, but basically I could just say, hey, I've got this array of 10 things all the time. I know the size, I know the length. As I mentioned, I have .length available there. And again, this array is its same size. Okay, interesting enough. I mean, the only thing that's truly perhaps interesting is these are, remember what we learned here, all of our integers are going to be initialized, so everything here is a 0 in our 10 integer array, and the brackets here are on the other side, right? From if you're coming from C and working in D. The compiler will almost always tell you, hey, you got to do things the D style way, not the C style way. If you make this mistake, I still make this mistake, but there you go. Okay, let's get into dynamic arrays. So this is built in, which is nice. If you're coming from C++, where you have standard vector or std vector, we have this built into the language. How do we have this built in? Well, you just don't specify the size. That's it. Simple as that. And then what you can do is you can append. Okay, this might be a little new thing here, but let's zoom in on where my cursor is. That's the tilde marker. What is the tilde marker? That's this thing, the little wavy sign, just so you can see it. And that's doing the concatenation, okay, into the array. So I'm appending an element here to the back. And that's as simple as that, which is kind of neat here. You can do some other stuff here, like here's my dynamic array of size 10, where I'm explicitly saying, hey, give me a new collection of those 10 integers. This is kind of like malloc in C, but again, as we're going to learn, this is garbage collected, so I never need to do free. There are no memory leaks in this program. The garbage collector will clean up when it needs to, or otherwise when the program ends. And then I can, still append more elements to it because it is dynamic. So I don't need to mess around with the realloc function or anything like that. It's just going to handle it for me, which is nice. And I can do similar operations with multidimensional arrays. So here's a multidimensional array below. There's a bunch of other neat array-wise operations you can do. Again, if you're coming from a Python world, some of these might be familiar. Let me just make this a little bit bigger so you can see it on the screen, maybe more easily, depending on your monitor size. But anyways, you can see some fun things like this, A and B, 1, 2, 3, 4, 5, 6. I can just assign a bunch of things to 0. I can, multiply these, do the products computed, basically get the dot product. So anyways, there's interesting operations that you can do on arrays as well, if you're doing like a bunch of computations or graphic stuff, and so on. All right, slices, another feature that's hard to live without, a neat thing in the deprogramming language, but basically the idea is, what is a slice? Well, it is a view into an array. So look at line number 8. I've got an array 1, 2, 3, 4. I could take a slice of it, 0, ... to 4. So that would mean the 0, 1, 2, and 3 index, that whole array here. And it's a view. So if I change the slice here, which is viewing into array, if I change the 0 thing at 50 and I write that out, right, it changes it for both of them, right? It's basically a pointer into that array here. But what's that pointer doing? Well, that pointer is a dynamic array, this slice, and it's got the pointer in the length here, right? So when I write it out, that's why it's printing out here. Now next experiment, down here at line 20, I'm going to make a copy here, and there's a .dup for duplicate, and that'll copy the array. And this time if I just change the copies value to 7 and write it out, the original array and the copy, right, the copy is its own separate memory. Okay, so there's a nice article. This might take a little tiny bit getting used to, this idea of what a slice is, but basically it's just like a pointer into an array that knows its length and the actual data that it's pointing to, okay? And again, why is this handy? Well, if I have slices, I'm avoiding copies and I can mutate data, and it's bounds checked, right? Because I know the pointer and the length. Okay. What else do I got here? There's a little shortcut. If you see the $sign, that'll get you the end of the array, so you don't have to remember. I could have used 0 dot dot $sign. The $sign would be a 4 there. Yeah, that's just a few notes on this. As mentioned, there's built-in associative arrays. They work. They're unordered. Again, in Python, you know these as dictionaries. In other languages like Java, you know these as hash maps or hash tables. But the basic idea is your key you specify within the brackets here. And then the value is, well, whatever the type is here. String. So key is an integer, and the string is the value. Okay, so 1, 2, 3, 4, 5, maybe that's my like student ID or something, and then the value I'm going to set to Mike, and I can write out my associative array, and you'll get something like this: key value pairs. And again, this example here is just to be really explicit, so you can study it a little bit if you find it helpful, where I have the key and value pair for these, this animal dictionary here. Okay, and I can do stuff like check if a dog is in the animals associative array here, and it'll write out, yes, dog is here, and then maybe write out what the dog does. Okay, so that's the idea. They're built in. They're very nice. They're similar in C++ to unordered map if you've used that, or again in Python they work basically the same way. Okay, what else is here? I think that's just a few more notes here, so we'll keep moving on. And again, you have the conveniences like .length and so on to retrieve the length of the associative array. There's .get as well if you want to just sort of test if something's available. So again, these are just some notes as you use associative arrays if you want to see what's going on. Okay. Let's go ahead and take a look at strings and character arrays. We had to write these ourselves, but again, these are built-in type in the D programming language. Strings are basically immutable character arrays. So what does this mean? I can do something like create a string, the symbol name Mike, and assign it to whatever I want, Mike. It'll be null terminated, so I don't have to worry about that. We already know what the string is here. I can write it out, but it is immutable. I can't change the string, so I have to reassign it. I either need to reassign it or, again, duplicate that string to use it. Again, this is just one of these like safety things, because we tend to operate on string data, maybe from multiple places, for whatever reason. So we want to make sure that there's clear ownership over the actual string if you're mutating something. Okay, so that's just a little idea here on strings, but they're built in. They're basically arrays. They're built off the type of arrays. So concatenation and doing these types of things will just generate a new string that you can use. So again, that little tilde marker, will just concatenate strings. All right. Okay, ranges. We already touched on these. Arrays themselves, dynamic arrays, or even fixed arrays are ranges that you can iterate over. We have for each reverse. We can use regular for loops, but I'm showing you the more exciting stuff, and you can do other stuff like, choose the value or just a slice here. But anyways, these are some of the tools that you have available. Okay, so hopefully that gives you a quick review of the language so you can figure out how to use it. Now from a memory perspective, let's get into some of the systems stuff here. Again, as I mentioned already, D is a garbage collected language. Here you can see I'm just allocating here with new, and then D will clean up after itself here. And I get a nice array here with 0 initialized memory here. I still have pointers. All that stuff we learned about pointers is exactly the same in D. So you can get the address of, you can create pointer types. That's all familiar. But again, D pays extra attention to memory safety here. So for example, this is kind of a neat thing to take a look at in this example, but I have this safe function here, and I've annotated it with @safe here. What does that mean? Well, the first and foremost, you see I've commented out line 7, which means I can't call into unsafe code. What is unsafe code? Anything that's not annotated @safe. So this one's annotated @system. That's the default in D that we have basically at system. Our main is @system as well. So I can't call a safe function into something unsafe. Now there is a bridge between it that's called @trusted, which means I verified this. So safe code could call into trusted, but otherwise, the compiler will give me an error here. And this is one of the ones, since we're talking about modern languages, I will again do a little bit of a live demo here. So let's just go ahead and code this one up here. Let's call a safe function, and we'll just kind of build this up here. Let's just go ahead and have our unsafe function, and let's comment out some of these lines here, and something like this here, unsafe, and I can annotate it system if I want here. And let's see what the compiler does for me here. Let's just go ahead and try to call unsafe here. Okay, so let's go ahead and just run this, and this is the type of error I get. Error at safe function exercise.safe. That's the name of the file .safe here. D has a module system. There's no headers. We just write .d files. That's why you get this full name here. I cannot call into at system function here. I could do this though. Let's just go ahead and save it. This is fine. Now it's working, right? Our program's doing whatever our program was doing here. Which let's comment some of this out here. This is our example 2. Okay, just so we can play around a little bit more here. All right, let's get rid of all that here. Okay, so anyways, that's the idea here. Now let's go back to the unsafe thing here. Let's put my folds back in. Sorry. Let's go to at system, and again I can do that here. What kind of unsafe other stuff that I'm not allowed to do here? Like, let's just create a pointer here. New int. I'm gonna heap allocate this, and let's try to do something like let's see if I can return this pointer here. Okay. I gotta make sure I write the function right here. Let's return p here. That's okay because this is heap allocated. Okay. Let's try to do something like p equals p plus 1 here. It says pointer arithmetic is not allowed in at safe function. So that's kind of interesting, right? There's a design decision here to say, hey, usually we mess this up or code evolves. So, make sure you're at least at trusted, which let's see if we're, do we trust ourselves here? Trusted. Make sure I save. And now we can do this, okay? Because somebody else has come in here through code review, professor, your TA, etc. Some other software engineer, and they say, okay, yeah, we think this works. Or if you get a bug in GDB, right, you look at your trusted or system functions and say, hey, something could have gone wrong there. So that's kind of one of D's answers to safety, to provide these annotations, right? This was something that was annotated in. Okay, so anyways, that's just something to keep in mind here. So let's go ahead and just comment some of this stuff out. Let's see from our unsafe function, can we do just like totally anything? Let's see if I can just, like return an array here. What are some bad things that we've learned of? Like local, like, I don't know, stack allocated thing here. Let's return stack allocated variable here. Okay. I mean, this is kind of interesting. I mean, I said this is at system where I just told you like, hey, anything goes. But the decompiler is smart enough to say, hey, returning basically a stack allocated, right? Because fixed size arrays are local variables. If I try to return that, even though I'm returning it, with this dynamic array thing, this is going to give me a slice back here. It's going to say, that's a no-go here. So D has some of these nice built-in protections from you in the compiler here. If I wanted to return this, how would I do it? I'd have to like make a duplicate, right? So it's its own unique thing. Okay, that way I'm always getting new memory. So these are the types of things that you learn sometimes by using another language. And even if you go off and use, C++ or whatever at your job, you'll have learned or hopefully have built in these habits here. And again, as maybe compilers in other languages get better, capture these errors here. But I think as the tooling continues to improve in languages like, since we're looking at D itself, you could use some of these, annotations again to build tooling around. And again, there are some tools for this, to play around with. So that's part of the safety story here. Now, there's an important moment in history in D here. I'll let you watch it yourself. If you have time, you can click on this. And this is Walter Bright. He's talking in 2017 at one of the D conferences. And basically he turns to Scott Myers, who's this gentleman here in the C++ world, and they're asking about like, what's the future for the C programming language? And Walter predicts that memory safety is the thing that's going to, basically eliminate or make C, not the language that people turn to early on. And basically we've seen this a few times in this course where we've referenced like what the recommendations were from various government agencies about using C and C++. So systems programming languages in the C and C++ world, or I should say C and C++, rather have been moving to try to add a lot of safety features, because that's true. Languages like D and Rust are here, which are memory safe languages. So and there is a follow-up on this at the D conference 8 years later, where you could hear Walter talk a little bit more about this as well. So anyways, that's the idea here. Now, some of this stuff I'm going to, again, go through warp speed. We don't need to know about pointer. I mean, we already know about pointers here. But again, I give you a few more slides on it. We know about the stack and the heap. Okay, so hopefully we know about this. We did a full lecture on this. Again, these are just my notes, again, on what is okay and not okay. And again, this is just talking about the stack allocated example that I just did. Now, in D, again, I talked about it being garbage collected and memory safe, but you can just use malloc. So most of the C standard library, you can just import in core.standard.c, and then, whatever the C library name is that you're used to using, standard lib, something like that, you'll probably find, and you can just call malloc. And again, you can see the explicit cast here. We use the keyword cast, so we know when we do this in code, oftentimes it's a sign that something interesting is happening. So we have that, but anyways, you could just do your regular malloc, and because you're doing your regular malloc, the garbage collector is not doing anything, so you must free that memory. Okay, and you can use Valgrind and so on to catch these errors, but again, you have to know, you're expected to know what you're doing if you're calling into the C library's malloc here. Okay, and again, just to show you that malloc's actually being called, if you look at that memory, there's garbage in here, right? It's not zero initialized. You'd have to use calloc and so on for this. All right, so anyways, this little example here, and you can see me looking at the memory by using the little slice. I mean, it's just regular memory at this point, and you can use all of these features like slicing and for each loops and stuff with this stuff. Okay, now, because sometimes we do forget to free our memory, we let's say we have to make a really large allocation. Okay, here it's 10, but something large enough where you'd want to justify, using heap memory. Let's say, a million bytes or something. I don't know. A gigabyte of memory. For whatever reason you want to allocate within your main, and then you want to make sure that you free it within this scope. So in D, there's this nice statement here, scope, which basically says at the exit of this scope. So what does that mean? At this curly brace. Well, where is its matching curly brace? Here at line 24. It'll call the free function here on the memory that you've allocated. Okay. In some languages, there's a statement here called defer. That's one way you could look at it. But in D, we have these scope statements. We actually have scope as a qualifier as well, which will, very explicitly make sure that heap memory only lives within the scope of something like a function, or here, for instance. But this is called a scope guard. Okay. And again, if you get rid of my comments here from line 7 through 13, what's really nice about this is the site of my allocation, I'm also describing what I want to do when I leave the scope here, which is free it. Versus if I put this free statement down at line 24, okay? So that the code that I write, the context is kind of kept. Here's what I'm allocating. I need this chunk of memory, and then I want to make sure I free it. I don't care really when, but I definitely want it within the scope here. But that way, then I can just kind of write my neat code that's then using memory without cluttering it up, so to speak, or having these two things that should go together, be out of context. So this is again the context of RAII, which we've discussed in class. Resource allocation is initialization, where you can do this. Now I could wrap this into a struct and do this as well. That would also be okay. But anyways, that's the idea here. Okay. Now, talking more about memory as well, we have, garbage collection does cost us something. We do have to pay for this garbage collection cost. So you can see what the message is here for a moment. But a garbage collector basically has to be tracking every time I do new and then figure out, well, when do I free the memory? Now, in D's case, the garbage collector is really simple. It'll free memory when needed. So it doesn't really slow the program down, so to speak, other than when I do the allocation, I do need to track the references to it. So there is some cost, so to speak, but I can turn that off or again use these annotations like @nogc. Now, if I use @nogc on my main and say, hey, don't garbage collect ever, I mean, I can't even use some things like write line. So we don't usually use it in that form. I'd have to call like printf or some, IO function that statically allocates a buffer of memory or something. But this is the idea here. That with @nogc, I can turn on and off the garbage collector. Okay, so you have some control over these things. This is a great talk. If you're going to watch another talk focusing on the systems aspect, which is what this talk's giving you a preview of in the D programming language, you should watch Walter Bright's talk here on memory allocation strategies, because he talks about malloc and free, the garbage collector, reference counting. He shows you in a slide how to build a reference counted type. If you don't know what that is, you could check this out. Get curious about these, because these are things that are going to show up in every programming language, from here on out that you use, or if you're concerned with performance, you just need to know these things. But this is anyways a really nice talk here showing the different strategies that D has. So feel free to check that out. I'm just putting in this note here because we talked about memory mapped files, and in the D programming language, there is a little library here for memory map files, so they make it kind of nice to use here. So anyways, I just did a little example here, but you can otherwise call into C functions as needed. Okay, got a few more things to show you. I'm trying to zoom through this. We're going to be like 30 slides short probably, but that's okay. D has built-in unit testing. What does this mean? Well, in the C assignments that I've been giving you as students, I usually just write a function or something, or give you a separate .c file that has a bunch of functions that'll use maybe code or a library that you wrote. In D, we could just put these unit test blocks. And the words of our author, book author of the D programming language, Ollie Trelli, he says these are comically underpowered, meaning they're very, very simple. We don't have a lot of other like fancy things, but by making it very, very simple to write this unit test and just asserting like, is this true? You actually write tests in your code. I have some more examples elsewhere, but this is a good enough example here. You can find it in the unit test where you create some type here, something like a vector3 type here, and then you can just test in line here. Is this computing the dot product, or doing the right sum or whatever, or being converted to a string here? Okay, so that's kind of neat here, and you can just do these in line. These actually do in D. You can generate documentation for your code with a tool called ddoc, the documentation generator. And these will actually show up as examples in the documentation. So there's all sorts of other cool stuff in the language there. Okay, so I'll get to a few of the object-oriented programming things, but again, we're running sort of short on time here. But again, we have all the object-oriented stuff if you've used that. I would say D is closer to Java's object-oriented, meaning you have things like interfaces, you have inheritance, but only one level, single inheritance, no multiple inheritance. You have things like public and private and so on. One thing to get a little bit used to in the encapsulation layer is that everything is public by default. I like this. Some people don't. It is just a thing that you have to get used to, but everything is available within the file in that you have. So if I create this game entity class here, if I make something private, I can still in a function later access m.name. So just a note about that, because the module itself, meaning the .d file, is the level of encapsulation, which I actually think is the right choice. In C++, otherwise you have to worry about things like friend functions and stuff. And again, I think module level is a right level, but that's an opinionated take here. So anyways, I just want to give you a preview on some of this stuff here. Have encapsulation, you have interfaces. So interfaces are just basically saying, hey, I have this type and it needs to implement these member functions. So if you want to implement a game entity, I need the interface for a game entity, which I usually prefix with capital I. That's something, again, it's a convention some people use, and then I have to implement those functions. Okay, otherwise the compiler will yell at me. But then that's nice, because then I can just create a collection of I game entities, and then anything that inherits or implements that interface, I can, instantiate, okay, as a new game entity in this case, okay? So you have a lot of polymorphism, these types of things that you'll learn about. Okay, so I already talked a little about interfaces here. This is where I'm going to go through warp speed. And again, D tries to protect you by learning from other languages, no multiple inheritance, because this causes problems of ambiguity, code complexity, and so on. You're not really missing out any feature. And again, I'll repeat this for the umpteenth time. D is a systems programming language, so you can basically do anything with it. This is true of any systems programming language: Rust, C, C++, D, Zig, etc. If you have access to the pointers and memory and structs and functions, you can re-implement these features, but it makes it a lot harder to shoot yourself in the foot, so to speak. Okay, so anyways, what about structs? We have these in D. They use RAII, which we have used, so you have constructors and destructors. The constructors themselves just have this keyword. Other languages, you have to match the name of the type here. I actually really like this. And then destructors have the little tilde mark, and that's what will be called automatically when this object is destroyed, whether by the, structs are deterministic if they're on the stack, so that when they leave scope, this destructor will be called. Okay. Classes and structs are different. Structs, again, are basically value types by default, and classes otherwise have reference semantics. So some of this stuff, again, goes back to like way earlier in the class when we learned about our systems class, pass by value, and what that means, and how we would do like pass by pointer as well. So the semantics of the actual data structure when you choose them matter. So structs are these deterministic structures when they're allocated on the stack, or we know where their constructor and destructor will be called. Structs don't have things like inheritance, classes do, and by default classes are treated as reference types, okay, versus structs, which are default value types. Now there are ways to get them to behave in different ways, which are what these examples are going to show, which I'd encourage you to try. But here's where I have a struct, my struct. Here's where I have a class, my class, and again, some of the differences between them. Okay, I like this mostly because in D, let's say versus C++, class and struct in C++ are basically the same. There's a little difference with how they're treated with the public and private defaults in classes and structs in C++. But in D, classes and structs are very much different. There are ways to define new types, and you can have member functions and member variables as shown here. But again, you make a decision up front about why they're, what their semantics are. And again, you can read what the semantics are in the bullet points here. Okay, so you can do a few of these exercises here by pausing the video. And, these are things, if you're getting excited about the deprogramming language, like try these out just so you can understand how the language is being used. And it's really cool to know how these tools fit together. They fit together just so nicely. So anyways, touching on some of our reference versus value type stuff here. Just very, very briefly, again, to reiterate here, what's going on in these examples, okay? All right, so I know I intentionally prepared more slides than I know we'd be able to get through in the 75 minutes here. So I just want to get to some of the last cool things here. Again, you can learn about the RAI, but basically, let me get into templates. Just because they've shown up a little bit, you've seen these like exclamation marks that show up. And basically in languages like C, you have like, there's no overloading. So if I want to write an add function for integers, I call it add I or add F, something like that. I need a new name. Now that's actually kind of nice. I like that when I'm debugging, but sometimes it is nice to just say, hey, here's the add function, name it the same thing, so I don't have to remember like what the suffix is, and then it'll just call the right one based off the types. That is kind of nice, okay? But we can improve on this and we can use templates, okay? So what's a template? That means like write the function once here, add, And in D, we just add a second set of parentheses. So the first one, T here, just represents the type. And then it'll basically do a textual replacement here of that type. So at line 10, when I see the exclamation mark and with int here, you can basically just take that int here, where T is, and copy and paste int. The compiler will generate a version of the add function for integers. And if I move out of the way, it'll generate a version of that function for doubles here. Okay, so that's really, really nice. This is how we enable generic programming in the D programming language. I like it. The parentheses are easy to parse out, and the exclamation is also easy to parse out. And you can optionally put parentheses here if there's only one argument. Okay, so you can see a few of these examples here. This gets into the generic programming stuff, which again, I think is really, really neat. And you can add aliases too if you really like that add I function here, and just the instantiation for the template, add exclamation int. So you get the idea here. Of course, you can add multiple template parameters, and auto just deduces the type for you, which is really nice. So if I accidentally have like an integer and a float value, it'll pick the right one and say, okay, well, if we're going to do additions between an integer and a floating point value for whatever reason, make sure we at least get a floating point type. Okay, so it'll do the right thing. You can, with this, add various, what's cool about templates is because they are at compile time being generated the code, you can add constraints on them. Again, this is a really important concept in systems programming, where you might want to say something like, hey, if I'm calling the add function, make sure it's a basic type, okay? Because I don't want to accidentally add two strings together. Semantically, that doesn't make sense, right? Mike plus Shaw, yeah, that's cool. Yeah, we want to add that string together. But like the add function, no, we want to call concatenate, right? So I can have this template constraint. In other languages, we call these concepts in C++, but in D, it's just a template constraint. It's just regular code that executes at compile time and should be able to tell, hey, is this type T that we pass in a basic type, an int, a double, etc. So if they fail, then you'll get a really nice message here, just a simple like, why did it fail? Because it had this template constraint here. And of course, you can specialize these things and do other neat tricks here. The last thing I guess I should show you is string mix-ins. And these are a really powerful feature where basically I can just mix in regular strings of code. It sounds like a really silly feature. I didn't get this for a long time. You'll have to come take another course with me or watch some of my YouTube videos to get the full power of mix-ins. But basically, it's an ability at compile time to mix in or generate code. So this gets into really cool styles of programming. Second to probably Lisp, D is probably one of the most powerful languages at what you can do at compile time, at least in my experience. I've looked at a lot of languages, and D is certainly at the top there. But basically, again, mix-in is basically a way for you to take strings that you generate, perhaps at compile time, turn them into D code, and then the compiler will check that code, make sure it's valid D code, each mix-in, and then you can basically execute your program. So, I mean, in this particular program, I'm doing a mix-in of importing some text file. The text file, which you see on the left, is this actual templated data structure, and it's just literally mixing in that code, okay, from some other text file, okay? But I can do stuff like run a loop or something at compile time and generate code. So there's some cool stuff you can do here, and you can, mix in various templates and make that generated code templated and so on. So anyways, we're at time here. I'm just going to flip through the slides so you can see them for the recording. In my game engines class, I think I show you how to do a serialize, basically for our struct, generate all the getter and setter functions automatically. But you can see how I'm kind of building up these strings here by using a feature called compile time reflection to basically look at a type and then gather all of its fields and then generate a get and set member function automatically. So you don't have to write that code, right? These are things you could do potentially with so a lot of work with the C preprocessor, but they're just built into the D language, so it's really, really nice. Like, that's all the code here. So okay, I mean, we basically got through it. I'm going like 40 seconds over, but hopefully you enjoyed this. Let's see, we already talked about allocation stuff, so check out some of the videos if you like D on YouTube. So this is my series here. Otherwise, there's a free book. Ollie Charlie, who came and has spoken at Yale University twice now with Steve. That's a nice book if you're doing your problem sets and want to check out. The forums are also a great resource, and you should check those out. Here are just some other inspiring, things to check out. So, anyways, with that said, we did it. We did a crash course. I know that went fast, but hopefully you're getting excited, or it's just cool or fun for you to look at a modern programming language. Try out D, try out Rust, try out some of these other languages, and see if they improve your your C code, even if you go back to C, if you prefer that. That's great too. But I'd really encourage you to expand your mind and start thinking about some of these things: ownership, safety, the transitive calling of functions, and how errors might propagate and cause these sort of tainted values to propagate and things. Even if it's something as simple as like nan as a default value for a float, right? That's like a very basic kind of taint analysis type of thing that you can also look up. So anyways, folks, I hope you had fun. Sorry I couldn't be with you because I was sick, but anyways, hopefully I'll hear some folks also getting excited about these languages. All right, until the next time, I'll see you soon.